So we're back. Physical Science 102, Chapter 22, Minerals, Rocks, and Volcanoes. This is going to be part 2. So if you started this one by accident, then you may want to go back and look at the other one that includes everything up to this point that I'm going to start out now, part 1. Okay, so let me share the PowerPoints and make a slideshow. Here we go. So that's where we left off with part 1. Now we're going to pick up with volcanoes. We talked about the 3 types of rocks. That's where we left off with part 1. And we were looking at the various types of igneous rocks formations. Now we're going to jump into volcanoes. Okay, a volcano, the definition from your authors is that it's a hill or a mountain formed by the accumulation of lava and volcanic rock fragments ejected through a vent in the Earth's surface. That's true for a great many volcanoes, but there are some volcanoes that do not leave a mountain or a hill behind. So what would cause that, right? If you have lava escaping the surface and it just kind of flows out, yeah, it'll eventually build up into a hill. Or if you have an explosive volcano that blows pulverized lava into rock and it settles down, it tends to form a cone, maybe, right? Okay, I agree with that. But there are some types of volcanoes that are so massively destructive that all they leave behind is a huge hole in the ground. Some supervolcanoes are like that. Yellowstone Park in northwestern Wyoming is a good example, right? You'd never know that that was a volcano, right? Because it just doesn't look like one. But it is geologically active, and it's been determined through research of many scientists over many years that Yellowstone is simply a supervolcano that's been inactive for 600,000 years. It's ready to blow again. And other events have been shown to be related to that particular event, and it's too much detail to go into right now. But my point is that volcanoes don't necessarily show themselves as hills or mountains. And there's also the influence of erosion, right? If a volcano goes extinct or it's quiet long enough, erosion can bring it down to the surrounding landform, right? So you may not even know it's there or that it was ever there. All right. So what do volcanoes do, right? They eject stuff from the interior of the earth to the surface of the earth. And they usually occur in 3 different forms. This stuff, gas is one of them. Right? Gases are always trapped under the earth. And if the pressure is high enough, they will actually dissolve in the materials of the earth, as long as there's pressure on them. Right? Just think about this. If you buy a 2-liter bottle of pop, right? What happens when you open the lid? It goes, right? There's gas under pressure. And then you see bubbles form in the liquid because there's gas dissolved in the liquid. When you release the pressure, the gas comes out. The same thing happens with lava. When it reaches the surface of the earth, pressure is off. And if there's any gas dissolved in it, it will come out, sometimes explosively. Then there's the lava itself, the molten rock. And third, but not least, is solid rock. So when the lava reaches the surface, if it erupts, it can also pick up solid rock. It doesn't have to melt it, right? It can melt it, but maybe it doesn't melt it because now it's starting to cool at the surface. So you can get gas, lava, and solid rock coming out of a volcano. Or when the volcano erupts, the gas may shatter or subdivide the lava in some form into smaller pieces. Now that they're liquid pieces flying through the air, they cool, and by the time they reach the ground, they're solid. So that's another way to form solid rock coming from a volcano. Gas, lava, solid rock. These gases tend to come out at all times. And the more gas that's available from underneath that comes out over a longer period of time, the less likely you are to get an explosive eruption. If you can get those gases out slowly, then they don't come out all at once and cause a major eruption and destruction. Slower evolution of gas is better. Okay, what are these gases composed of? Well, it's hot enough so that a lot of the gas is water vapor, right? Steam. But there can also be carbon dioxide and hydrogen sulfide, right? Both of these. In high enough concentrations, they are deadly. Carbon dioxide will drive out all the oxygen. So if you don't have a respirator with an additional supply of oxygen, then simply carbon dioxide may suffocate you. And that's been known to happen in the vicinity of volcanoes. It simply expels all the oxygen from the air and you suffocate. Hydrogen sulfide, on the other hand, in addition to expelling oxygen, hydrogen sulfide is a very reactive gas. In other words, it damages your lungs if you breathe it in. Hydrogen sulfide combined with water makes sulfuric acid, right? And that can do damage also. Okay, how about the lava? Well, it can come out of the volcano in various forms. If it's very viscous with not much gas in it, it may just come out and flow, like the Hawaiian volcanoes. They just open up a vent, here comes the lava, it flows out. Sometimes it flows underground through these lava tubes until it reaches the ocean, and then it cools and hardens, and more of it comes out. But if there's lots of gas in there and the lava, well, if the lava is free flowing, right, not very viscous, then even if it does have a lot of gas, it may be able to just come out and flow. But if it's very thick and has a lot of gas in it, it may come out explosively. Now, some volcanoes, when they erupt, they emit large volumes of solid material. This is collectively known as tephra. T-E-P-H-R-A, tephra. They can be of any size. Tephra could be boulder size, or they can be dust particles. One characteristic of tephra is that, as I mentioned earlier, usually starts off liquid. So when it's blown out of the volcano, it's still liquid. But as it spreads, it cools and falls to ground as a solid. Sometimes we identify some of that as ash. Now, if there's a lot of this tephra expelled, and it's very hot, there's no doubt about that. If it comes out liquid, it's hot. And once it cools down a little, but it's still hot. It's a solid, but it's hot. If there's enough of it, and there's not a whole lot of push underneath to blow it high, then it may come out and flow down the sides in what's called a pyroclastic flow. Pyro meaning hot, and clastic meaning flowing. So this tephra moves along the surface of the ground. That's bad for anybody that gets caught in its wake, because it suffocates, it burns. And if you've ever looked at these particles or seen pictures of these particles under the microscope, they're like little razor blades, right? You breathe that stuff in, it will chew up your lungs, right? So you need to protect your lungs if you are anywhere near this pyroclastic flow, or ash for that matter. Here's some tephra emissions, right, from this volcano in Guatemala. Central America is very volcanically active. Just put it that way. In fact, many of the Caribbean islands also are volcanically active. Okay, so how can volcanoes erupt? I've already mentioned several, referred to them. But basically, they can either be explosive or peaceful, non-explosive. Right? And it depends largely upon the viscosity of the magma. Right? So low viscosity magma tends to flow easily. So you get your Hawaiian type volcanoes, where the magma comes out and just flows down the sides. Right? It can still do damage. Right? It can flow through neighborhoods and just burn everything to the crisp. Right? Your house can go up in a smoke like that. That's low viscosity magma. Generally peaceful. In other words, you got time to get out of its way. High viscosity magma, on the other hand, has difficulty flowing and only moves under great pressure. So what that means is, if it's very viscous, then the pressure tends to build up and build up and build up, and it's not released slowly. It's released all at once. When it reaches a certain limit, it has enough force now to blow the magma out. That would be an explosive eruption, because more pressure is required to get the magma, the lava, out of the volcano. Okay. The viscosity of the magma is dependent upon two factors usually. What's its temperature? That's obvious, right? The higher the temperature, the more easily it flows. It's like molasses or honey that you put in the refrigerator. Right? Put it in the refrigerator, leave it there for several hours, pull it out, take the cap off, turn it upside down, nothing happens. It's cold and thick. But if you put it in, if you take that bottle of honey and put it in a pan of hot water, eventually it warms up. Now you can pour it out. Very easy. Magma is the same way. The lava that comes out of the volcano is generated by the magma viscosity based upon temperature and upon the content of silica. Remember, we talked about density of igneous rock based upon silica content. Well, the silica content can also contribute to whether the magma flows easily and comes out of the volcano as easy flowing lava or explosive lava. High temperature, low viscosity, flows easy. Right? These magmas generally originate deep within the earth at higher temperatures. So as they move to the surface, they don't cool very much. They're higher temperature, they flow very easily. The higher the silica content, the higher the viscosity. It's more difficult for the magma and the lava to flow if the silica content is high. These magmas generally are created at shallower depths. They have a higher silica content and lower temperatures. So you get explosive volcanoes, like Mount St Helens, for instance. So when you have a peaceful eruption, these magmas tend to be basaltic, low silica. Right? We mentioned that earlier. They're going to have low silica, they're going to be darker in color, they're going to flow more easily. And they originate from deep in the earth. All right, so all these things combine together to make a peaceful eruption. So we also can define basaltic rock as volcanic in origin, and it has a content of around 50% silica and less than 5% alkali metal oxides. So alkali metal means what? Right? Remember your periodic table. Alkali metals, sodium, potassium, primarily. There are other alkali metals, but these are the common ones, the most abundant ones. Oxides of those metals. So the point here is that it may be low silica, but it's not no silica. I mean, there's still silica there. It's just low silica. This is basaltic Hawaiian lava rock formed from their peaceful eruptions. Okay. Let's see. We're still talking, now we're talking about basaltic eruptions only. These are the peaceful ones. These types of eruptions occur in two types of geologic settings. One is they occur along the length of a divergent plate boundary. In other words, two tectonic plates are moving apart, which means the crust now is thinner and the underlying magma can push its way up. Right? If we thin the crust, there's less pressure above and it pushes up. Those are divergent plate boundaries. The Eastern Rift Valley of Africa is one example of that. They often form these volcanoes, extinct volcanoes, most of them. Some active. There are three types of volcanoes. Usually they're either active, which means they erupt every few months or few years. Dormant means they haven't been noticed to erupt in a lifetime. Or extinct volcanoes. And they've never erupted ever in anybody's lifetime. Right? So the Hawaiian Islands, two distinct settings. One is divergent plate boundaries, and the other is hotspots. Let me clarify myself. Divergent plate boundaries, right? So you get this plate over here, and the plates are moving apart. So the magma comes up in those areas and just fills it in. This is a relatively peaceful type of eruption. Or you have hot spots. Hot spots can occur anywhere. The Hawaiian island chain is an example of hotspot that has existed in the Pacific plate for thousands of years, hundreds of thousands of years. So you get the Hawaiian Islands form, and then as the plate moves, that island that formed is moved off of the hotspot, and a new one starts to form. In fact, the big island of Hawaii is still somewhat active, but there's already a new one, a new island forming southeast of the big island of Hawaii. It's still under the ocean, but it's forming from a hotspot. And this is generally attributed to a mantle plume. That is, the mantle is relatively thin, and you get this magma moving up, and it's breaking through the crust. This rising magma tends to be stationary in the asthenosphere, and the crustal plate over it tends to move across that hotspot. So the hotspot is relatively stationary, and the overlying plate moves, and that gives you this series of volcanic islands. Here we go. So here's the Pacific plate moving across this hotspot. And now here's the latest Hawaiian island being formed. And here's a chain of other islands that formed in the geologic past. Why are they smaller? Erosion. Over time, they may have been as big as the big island, but over time they've been eroded, and now they're smaller, smaller, smaller. Some of them in other hotspots are so eroded, now they're below the surface of the ocean. Or they may form atolls, right? Just rings of islands around what used to be the central volcanic island. Okay, how about the explosive eruptive types? These are silica-rich magmas that reach the surface. They're lower temperature, higher silica, which means they're thicker. They generally originate around a subduction zone. So one plate diving underneath another one. So what happens is this plate is moving over this plate, and it dives down like this, right? So as this plate moves underneath this plate, as it goes deeper, it gets hot, it melts this, right? And reaches the surface as a volcano. The Cascade Mountains of Northwest United States is an example of that type of volcanic activity. And they're very explosive eruptions. Mount St. Helens, I keep mentioning that, but it's a perfect example. Mount St. Helens event back in 1990, I believe it was, blew the side out of itself. I've got some pictures coming up. These magmas are high in silica. And this subduction usually occurs, the one plate, the ocean plate, is denser, higher in silica, right? So it dives underneath the lighter continental plate that floats above it, right? And remember, the oceanic plates are higher silica, they're denser. So they dive underneath, and when they produce the magma, they obviously produce this explosive type of lava. All right. Andes Mountains, right? They're also these types of mountains produced from subduction. And here's a picture of Mount St. Helens after the explosion. We're looking at it, we're on the north face, right? Looking south. Oh, okay, I got a video coming up. So let's see, do I need to click it? This is a composite sequence of several still photographs that show the collapse and explosion of Mount St. Helens. That's something. There it goes. So what you're seeing is a landslide, right? There was magma lava activity underneath the volcano that was making it shake. And the composite material of the volcano was not real stable. So if you get a lot of rain on it, that lubricates it, or it's just not very well consolidated. So all you need is an earthquake to shake it, and weak spots cause it to slough off. And once that burden is removed, the pressure is off. And now you can get explosive release, which is exactly what's happening right in here. Remember, this is a composite from stills that was produced by the U.S. Geological Service based upon still sequence photographs that were made by this fellow right here, Gary Rosenquist. I think he was just a tourist taking pictures. Fortunately, he was far enough away from the activity, the action, that he didn't die. Several people died as a result of this explosion. And this is the north face, facing Canada. It's blowing that way. Okay, let's move on. Let's see, there we go. So this molten volcanic material, such as it is, once it reaches the Earth's surface, can produce different types of structures. It looks different on the surface, depending on how it was created, what its composition is, how much of it there is, and how long it takes to deposit. Various factors contribute to what we see on the surface. And again, it's largely dependent upon the composition of the material and the temperature of the lava. These are examples. You can get flood basalts, like we see on Hawaii, right? They just flow across the surface of the earth and solidify. We have shield volcanoes. These are volcanoes that are broad. They're noticeable, right? But they look like a shield just laying on the ground, right? This round shield. Captain America dropped his shield on the ground and it looks like a hump. That's a shield volcano. Stratovolcanoes, on the other hand, are more cone shaped. And if you take a cross section of them, they are stratified. In other words, they're layered from outside in. That's because when they erupt, the tephra that's expelled settles down, and then it gets quiet, and then erupts again, blows out some more, and it builds up over time. Sometimes they produce what's called a cinder cone. And then in the center, you may get a depression where there's still volcanic activity, possibly, but it's not actively erupting at the moment. And you can see this depression in the center of the volcano. This is called a caldera. It's often the result of a collapse of the magma chamber underneath the volcano. So while it's erupting, right, it's filled all this space with lava and tephra blowing out. But when it's finished, there's nothing to hold that stuff up. So it just collapses and forms this crater in the center of the volcano. There's some, especially extinct volcanoes, that may even be filled up with water, right? Over time, rain collects in them and forms a lake in the middle of it. Okay, fissure eruptions. That's like, well, I erased it now. Where the plates move apart and form a fissure and allow the basalt to come flooding up into that space along these long fractures in the surface of the earth. Now, these fissures can be very large, or they can be just large enough to let the basalt, the lava out, and then it just keeps flowing, right, outside the fissure. Large portions of Washington State, Oregon, Idaho are covered in multiple layers of these flood basalts. And they collectively combine into what's called the Columbia Plateau. That's where the Columbia River gets its name. These basalts are extremely fluid. They're what we normally consider a liquid. High temperature, low silica. And in this case, they covered an area of over 500,000 square kilometers. Right? So you're talking about 300,000 square miles. Right? Big, large area. And they're very thick, right? This whole plateau, up to 150 meters thick. Right? So this has happened a lot over time to make that thick. The nice thing about it is the soils that form once it stops and weathering can start taking place, we can form soils out of this stuff, and it's very, very productive, very rich soils. Okay, here's a road cut, right? A lot of information can be gained from road cuts because they'll cut through either soil structures, which is my line of work. I mean, I was trained as a soil scientist, so we would often look for road cuts so that we could see soil layering and structure. But if the road cut is through rock, then the geologists move in and they can gain information from that. You can see here these vertical lines, right, cut down through here. Those were drill holes for explosives, right? So they drill those holes, pack them with dynamite, and overpack them with AMFO, ammonium nitrate fuel oil, and blow them off. So these are artificially produced, those lines right there. Okay. The rest of it is natural. Okay, I mentioned shield volcanoes. They look like a shield. The lava is not quite as fluid as these flood basalts. Right? It's a little thicker, so it has a little bit more silicon in it. and it's a little lower temperature, but it still flows fairly well. It just doesn't cover a wide area as before. It tends to pile up as it forms. The Hawaiian Island volcanoes. Those are examples of shield volcanoes. Gentle slopes, right, also form from repeated basaltic flows. They're not particularly violent. They're peaceful eruptions. Right? Here's Kilauea on the big island of Hawaii. Very gentle sloping. And you can see in the middle here a caldera. It's a crater in the middle of the volcano. Stratovolcanoes. Now these are composed of alternating layers of, and maybe varying content of silica. In fact, they usually are. So you can see, if you can find a place where they split open the best, then you can see the layering in there. You'll see light, dark, light, dark, light, dark, which indicates high silica, high silica, medium silica, as the deposits are built up over time. These are generally the result of violent eruptions. They have the lava is thicker, right? It doesn't flow very well. So a lot of pressure has to build up in order to get it out of the ground. And when that pressure is reached, when the limit's reached, then you get the explosive part of the volcano. When you find a single solitary mountain sticking up out of a plain somewhere, it's probably a stratovolcano. And let's see, Kilimanjaro in Africa, in Kenya, is a perfect example of a stratovolcano. And that is a big one there. But others, Mount Fuji in Japan, Mount Shasta, Mount St Helens, Mount Hood, all in the Cascades of North America. And I mentioned Kilimanjaro. Those are all stratovolcanoes. They are the result of violent eruptions. There's Mount Shasta. Cinder cones, at least you may, the temptation is to consider cinder cones a form of stratovolcano. But they're not well stratified, the cinder cones. The cinder cones tend to be very small as compared to the stratovolcano structures. And they're largely composed of what we would consider to be cinders. And these, they used to, back when I was a kid, track and field building structures around schools had these racetracks, right? And in the center, you might have a soccer or a football field. And then on the sides, you might have other field events like long jump and high jump and so forth. But the track, for many years, was composed of cinder that was harvested from these structures, these cinder cones. And these cinders, or they could be the product of industrial activity. That's also possible. But they're generally formed in a similar fashion. In other words, the molten material contains lots of gas. And when the pressure is released, the gas comes out of solution and forms these gas pockets, some of them, and some of them explosively degrade the material into smaller particles. But high gas is typical. And the tephra tends to be lighter than you would see in the typical lava flow. These cones rarely exceed 300 meters. Right? So that's like 3 football fields long, stand them on end. That's about as high as they get. There may be reasons for that, possible reasons. These cinder cones are very young. They're just getting started. They may be formed in areas that are high erosion, like in the tropics, right? Lots of rainfall. So before they can compact and solidify, the rain just washes them off. Right? Here's an example in El Salvador, right? Definitely high rainfall, right? So this cinder cone gets eroded regularly. And over time, if the cinder cone goes dormant, it'll eventually be eroded away. All right, I mentioned the caldera. All right, here's a textbook definition. A large, roughly circular, steep, walled depression in the summit of the volcano. And it generally forms when the magma chamber underneath collapses. After the magma chamber has emptied itself in the eruption, there's nothing holding it up, so it collapses. I mentioned some of these calderas can be filled with water. Crater Lake in Oregon is an example of that. Let's see, do I have a picture? Yeah, there we go. So here's a caldera of a volcano that is filled with water over time. And it's very deep. 1,500 feet down, I think, is maybe, if I'm not mistaken, in places. All right. So remember, we had estimates of the strength of hurricanes and tornadoes and earthquakes. There's also a scale that's applied to the power of volcanic eruptions. The volcanic explosivity index is one of those. It's a scale that describes how big was the explosive eruption that has just occurred, right? And you can have several from the same volcano, right? So each eruption has its own rating. And they generally go from 0 to 8. 8 being the biggest. This is a logarithmic scale, remember? So from 1 to 2 is not linear. In other words, it's not 2 times as big. It's logarithmic in nature. And here we have some examples. Mount St. Helens was relatively small on a historic scale. We had 2 eruptions, right? The first, let's see, actually Mount St. Helens erupted several times. The first one was pretty big. Excuse me, that's not right. Mount St. Helens erupted in 1980 and again in 1980. And then it erupted, it recovered. And then 9 years later is the one I remember, the one that I showed you a composite of just a few minutes ago. So the one that occurred in 1980 was much, much bigger. How much tephra was blown out of the volcano, right? In terms of cubic kilometers. So this Mount St. Helens in 1980 was about 1 cubic kilometer. The Pinatubo volcano in the Philippines in 1991 was 10 cubic kilometers. Krakatoa was 100 cubic kilometers. Right, and they're big. It's estimated that the last time Yellowstone erupted, it was the biggest supervolcano, 1,000 cubic kilometers or more. Here's another way of looking at them. Some of these are estimates from prehistory. This big one here, Wawa Springs, I've never heard of that one. Supposedly occurred in 30 million years ago. And it erupted, it sent 5,500 cubic kilometers into the atmosphere. My guess is that several years after that, the Earth was kind of cool because it goes up into the stratosphere and blocks out the sun. Let's see, in recent times, Krakatoa in Indonesia was level 6, 20 cubic kilometers. Right, this 1883, there were witnesses to that one. Okay, oh, there's Vesuvius over here, right? That buried the Roman cities of Pompeii and Herculaneum. Right? It was on the order of about a 5. Okay. Oh, so we're going to get some details here. Tambora, 1815. The largest volcanic eruption that has been recorded in human history. So this one, we do know, put so much volcanic ash, so much tephra into the upper atmosphere that the following year, 1816, was known as the year with no summer. It just, you had New England in the United States, they had snow in June. Mount Pelée, this is on the island of Martinique in the Eastern Caribbean. Was a pretty sizable blast, and it killed 30,000 people. Largely from the pyroclastic flow. Right? The volcanic gas in Tephra, superheated pyroclastic flow caught people off guards. How about this one? Piracutin, 1943 in Mexico. They saw hot gases coming out of a plowed cornfield. And then the cornfield was destroyed as the cone built itself, eventually over 400 meters high. Surtsey in 1963, off the coast of Iceland, the southern coast of Iceland. I remember seeing newsreels of that one. It eventually formed a permanent island in the North Atlantic. Right? Remember, the North Atlantic Ridge goes right up the center of the Atlantic Ocean, and that's where plates are diverging. Right? New lava comes up, plates are pushed apart. Well, Iceland is a result of that activity. And this extra island, this Surtsey, is just another example of that eruption in plate divergence. Sofia Hills, 1990. Where is that? Oh, Montserrat in the Eastern Caribbean. This volcano they thought was extinct, but it was just dormant. After 400 years, it erupted again. Right. The capital city of the island, Plymouth, and the airport were buried in ash. Most of the inhabitants left the island or moved to the other end of the island, far away from the volcano. And then, of course, Mount St. Helens. Right? I forgot about this one, 1980. It blew itself up. It hadn't been seen active since 1857. So it was like 123 years was the last time it was recorded erupting. Right? More than 60 people. You know what? This is the eruption that we saw. I misspoke earlier. 1980 was the eruption we saw at Mount St. Helens on that video. And then the others were smaller. They were after eruptions. So it continued to be active, but the eruptions were smaller in nature. Mount Pinatubo in the Philippines. Right? It blew ash into the stratosphere. Forced the U.S. to abandon Clark Air Force Base on the, I don't know which island it was on, but it was probably on that same island. Okay, Mount St. Helens. The devastation reached as far as 8 kilometers, or about 5.5 miles from the summit. That would have been in the northern direction, I think. It blew down trees. It buried the region in ash and pyroclastic flow. The mountain was covered in snow. So it melted the snow and formed what's called lahars. A lahar is a mud river. It's got so much sediment in it that you can't even tell that it's a river, but it flows and fast and wipes out everything in its path. Came down the side of that mountain and through and down the rivers that led from the mountain. Right? So there you get, there's a picture of the destruction. You can see some of the trees blown down in the distance. I think I got another one that's going to fade in here in a second. Here we go. So there's a still photograph of the mountain erupting. Yeah, I misspoke earlier. This was the 1980 eruption. So if volcanoes are so dangerous, why do people insist on living in the vicinity of volcanoes? I imagine there are a number of reasons. In Hawaii, it's obvious. I mean, it's the tropical paradise, right? We're willing to put up with the danger. Other reasons is the soils, volcanic soils that are produced from these eruptions are very rich, very fertile. I mean, when they're first formed, they kill everything. But once plants return and start re-invading the area, they have a new source of nutrients that are delivered by the volcanic ash. And people will farm these areas. They're very productive. Okay. So now that we've covered volcanoes, let's go back to James Hutton and his rock cycle model. He was particularly interested in sedimentary rocks. These were very old in Scotland. And his concept of the sedimentary process is what drove his theory forward. He noticed the effect of water and wind on the rocks and the soils, how they eroded, how they tended to when the water slowed down, the sediments would drop out and start forming layers. So he reasoned that this was a process that could be going on for many thousands and millions of years and lead to the formation of new sedimentary rocks as they built up over time, compacted and cemented together. These sediments generally form in areas where the water has stopped flowing. So it may flow down into a lake or into a broad area of the river where it's not flowing very fast, and the sediments drop out. We do this with hydroelectric dams. Right? Whenever you dam up a river to access the power of the water in a dam to make electricity, the water that's moving into that artificial lake behind your dam has slowed down. It cannot carry the sediment load anymore, so it drops out and settles on the bottom of the lake. So over time, the lake tends to fill up with sediment. So if you want the lake to be navigable, eventually you'll have to go in and dredge it. Now, it all depends on how much sediment is being transported from the river into the lake, right? Some places there's not much, so dredging doesn't have to occur very often or at all. But in places like Egypt on the Nile River, when the Egyptians built the Aswan High Dam, they found that very shortly, just a matter of years, the lake behind the dam was filling up rapidly with sediment, and they had to go in and dredge it out. Okay. Hutton also observed these layering in the rocks that were exposed after a certain amount of erosion, and he noticed that they were composed of small grains, very often sand and other rock fragments. So he reasoned that this transport of particles by water and wind and settling out was what led to the formation of these rocks. All they had to do was compact and cement them together. Now you've got sedimentary rocks. So that was the basis of Hutton's theory. Here you have sedimentation that's shown this type of rock along the coast of Wales. Right? Everybody knows where Wales is, southwest of the English Isle. Galveston Beach. These sand particles are transported here by wind and water. Right? So sandy beaches, the ones that are naturally occurring, are formed from these eroded particles that are brought in by ocean currents, which means that they can also take them away. So if you have a hurricane come through and lots of wave action, you can erode this beach away entirely. Okay. Hutton also noticed one of his clues was the formation of strata, layering in sedimentary rocks. And this fit with his theory of the way sediment would be laid down in layers and compacted. The older layers are converted into rock because they are experiencing the weight of overburden pressing on them. Some of these sedimentary rocks are, over time, experience other forces from the earth that push them up to higher elevations. And when erosion, they form mountain ranges, and erosion will expose their surfaces and show you the layering in those rocks. Okay, sedimentary rocks are not that common, right? About 5% of the Earth's crust is sedimentary rock. But they tend to be very well exposed on the surface of the Earth. So that means that the surface of the Earth, what we can see, is about 75% sedimentary. Even though they're a minor portion of the Earth's crust, what we see is a larger portion. Most of the rocks in the Earth's crust are igneous, but we just don't see them. And some metamorphic as well. So the sedimentary rocks are a thin veneer on the surface. So weathering has occurred, and then sedimentary rock forms on top in a thin layer. So a lot of the things that we need to survive are produced and provided by sedimentary rocks. Petroleum, coal, fossil fuels, right? So what happens is the once living material is buried in thick layers underneath or within the sedimentary rock. And while in there, it undergoes chemical changes. It decomposes without the aid of oxygen, right? So it undergoes what we call pyrolysis, simply heating and modification, produces coal and other petroleum products like oil and natural gas. Some metal deposits occur in sedimentary rock. We often use sedimentary rock for construction too. Sandstone is commonly used in areas that have it available. What type of landforms do we see with sedimentary rock? Some of them are very beautiful. They have various colors, right? You can see them. In fact, I've never been there, but I've seen pictures and videos of Grand Canyon. Grand Canyon is a perfect example of sedimentary rock that has been eroded away. And the Colorado River, Colorado River has cut through the sedimentary rock down to a depth of 1 mile. So you can see layer upon layer upon layer of sedimentary rock. Now, the theory is that the river was relatively constant in its change in height from its origin to the ocean, but the landform was pushed up. So it just kept cutting down as the landform moved up. There you go. Colorado Plateau, which incorporates the Grand Canyon. Oh, there's a picture of it. And you can see different colors. And somewhere down there, way down there somewhere, we can't see it from here, is the Colorado River. Okay. The proper term for the creation of sedimentary rock from the sediments is lithification. Lith means rock. So it's just rock making, right? A fancy word for rock making. It involves compaction. You have to compress the particles together, and then some way or other, they have to be cemented together. Cementing agents. They can come in several forms. They can be calcium carbonate. This is a chemical reaction that produces calcium carbonate, or it can be a change in the silica at the surface of the particles that actually bonds them together. Or you can have iron oxides that are dissolved in the groundwater. And as the water moves through and the rock is forming, you can get water moving through with these various components, and they stick to the surface of the particles and bind them together. These are cementing agents. Okay, let's classify sedimentary rock based upon the origin of their constituents. Okay. Two main types of sediments. Detrital. That's what we would call particles that are blown or flow in with water to an area. That's detritus. Okay. The other is chemical. In other words, the formation of the sediments themselves are based upon a chemical reaction and usually involve the formation of a precipitate. Okay. There it is in black and white. Okay, so when we focus in on detrital sedimentary rocks, we're looking at the size of the grains that have been cemented together. Shales are composed of very fine grained particles that were initially muds. From my line of work, from my training, those would be usually silts and clays are compacted into shale. Sandstone would be a larger particle size, obviously sand-sized grains. Or you can get conglomerates. You can get very large pebble-sized materials incorporated in some of these other materials. That's a conglomerate. Well, I should qualify that. They're rounded pebbles. If they're angular pebbles, we would call them breccia. Usually these rock fragments, those rock particles, are held together by calcium carbonate or silicon dioxide cements. Okay, these are grain sizes in millimeters. Right? So you have to have the idea of what a millimeter is, right? To say, oh, it's about that big. So greater than 2 millimeters is a gravel. These are the rounded pebbles or the angular pebbles, the breccia. The rounded pebbles suggest to me that there's been a lot of water activity, which causes the corners to be rounded off. Whereas the angular pebbles are very young. They've been formed, but they haven't had time to tumble in water and erode to the point where the corners have been knocked off. A sand is between a 16th and 2 millimeters, form sandstone, and then the muds are less than a 16th of a millimeter to form shales. Okay. What about, let's see, that was, let's go back. That was detrital sedimentary rock. Now let's look at chemical sedimentary rock. It can form from either organic or inorganic sources. The inorganics are the easiest to understand. The minerals were transported in solution, that is, they were dissolved in solution before they were deposited. The organics are a little trickier to understand. So let's say the inorganics like calcite or halite. There's a correction here. Calcium sulfate and waters of hydration. This is not gypsum as written. This is gypsum, 2 waters, right? Just to be precise. Very often, these are formed from evaporites. In other words, the water flows in with these things dissolved, and then the water evaporates. And as the water evaporates, the solubility of the dissolved components decreases. And you concentrated. They eventually reach the point where they can't stay in solution, they drop out. That's an evaporite. Dolomite, that's the one I couldn't remember. Calcium and magnesium carbonate together, that's a dolomite. They can form from precipitation reactions. Inorganic chert, chemically precipitated silica. I'm not sure how that happens. There are other types, that the organic types, you can form calcium carbonate from marine organisms, right? Algae in a class of organisms called foraminifera. And they can form limestone. So their skeletons, they deposit calcium carbonate in a skeletal form. And believe it or not, some algae can deposit calcium carbonate. Let's see, they're not mentioning, they're not mentioning corals here. Right? Coral polyps deposit calcium carbonate as a protective shell. And that can form rocks. Biogenic chert, radiolaria. You have to see these under a microscope. Diatoms, sponges, some sponges you can see without a microscope. But their skeletons are formed of silica. Rather than calcium carbonate like corals, their skeletons are formed from silicon dioxide. And then there's coal. Coal's in here because we just don't know where else to put it. I mean, it's buried in the sedimentary rock, but it's not mineral. So we stick it in there because there's no other place for it. All right, this is the way organisms form the minerals that are deposited in sedimentary rock. They extract them from solution. Let's see. Yeah, I mentioned that already. Corals, one possibility. Bivalves, like clams, other types of mollusks will take calcium carbonate, and some will incorporate silica also in their shells, and they bring that out of the water, out of the solution, and deposit it. Then when they die, those parts sink to the floor of the body of water and eventually are incorporated into rock, sedimentary rock. Here's a good example. Organic limestone in the Everglades. You can still see some of the shells. Coal, it's classified as an organic sedimentary rock simply because there's nowhere else to put it. Inorganic chemical sedimentary rock, evaporation is the primary agent for sedimentation of these chemical compounds into sediments that form rocks. Sodium chloride, gypsum. Various cave deposits can be pure calcium carbonate. If you study them carefully, characteristics of these sedimentary rocks give you clues as to how the rocks actually formed. Look for the color of the rocks. What are the size of the grains and the characteristic of the grains? Are they sharp? Are they angular? Or are they rounded? Have they been sorted in some way? In other words, in the rock, you can see that the grains might be thicker down here than larger grain down here than and thinner grain up here, smaller grains on top. You can actually see them in bedding, the way they layer in. You can gain information from the fossil content. Now, fossils can be very large, like even bones. They can be skeletal remains, like those clams, or actually they can be microscopic fossil content. They can be formed from microscopic plants and animals, but they can also incorporate various types of distributive organs from even land-based plants that are blown in or flow in and settle along with everything else. I'm thinking in particular of pollen grains, for instance. You can even see ripple marks, right? So if you have a sediment come in and there's wave action on that sediment, then it can form ripples, and then another layer comes in and seals those ripples, and that becomes stored in the rock. You can see cracks in the rock. We've even seen fossil footprints from dinosaurs, from mammals, even human fossilized footprints. You can even see the evidence of raindrop prints in the rocks. If they hit the sediment and then are subsequently covered up without disturbing the impact, then you can form rocks that preserve those features. And they tell you something about how the rocks were formed. You can get all shades of colors. You can get different grays. They're very common in sedimentary rocks. This tends to indicate that the rock was deposited in shallow, well-aerated marine environment. The gray shades do. You can get yellows, browns, and reds. These are typically deposited on land above sea level and with the presence of abundant oxygen. The oxides of iron in particular, but also aluminum, will color these deposits in yellows, browns, and reds. Right? Just think of rust, right? Iron oxide is bright red. It's rust. A rich oxygen environment produces that color. So the browns and the yellows might be less oxygenated. Dark gray to black often indicate the presence of carbon. You can get carbon entrained in the sample, and it will blacken the rock. Now, that's not the only way that you can darken a rock, but that's one way. These tend to be accumulated in stagnant oxygen poor areas. So the carbon that comes in is not oxidized to carbon dioxide, for instance. Bright colors point toward terrestrial deposition. This is Devil's Kitchen in Wyoming. I'm not sure how this one happened, but you can see the reds here along the exposed cliffside here. Angular grains indicate that the sediments were not transported very far. In other words, as you transport these grains in winds or in water, they tend to tumble and they knock off their corners. So if they go a long way, the grains tend to be more rounded. If they go a short way, then they're more angular. If the grains happen to be very large, sand-sized grains, for instance, they were transported by very strong currents. Right? Probably not by wind, but possibly by wind, more likely by water, but strong currents, because the larger the grain, the more energy you need in the transport mechanism to keep them suspended. Right? And this goes back to a physics law called Stokes' law, which is used by hydrologists to determine how fast the water was flowing during a flood, or how high the water was, what size rocks were moved. We used to use it in soil particle size analysis, because the large grains would settle faster and the small grains would settle slower. And we could use that information to tell us something about the particle distribution in the soil itself. Small grains mean that the transport mechanism was very weak, and that the environment was relatively calm when the sediments were deposited. Sorting may occur during this deposition. You may be able to separate sediments by particle size. So if the sorting is very strong, very specific, then you can get noticeable uniformity of particle size in the rock itself. Right? If you get a mixture of sizes, then you know that the sorting mechanism was not very effective. Well-sorted sediments indicate that the sediment was transported for great distances and it took a long time to get there. Whereas poorly sorted sediments that have a mixture of grain sizes indicate very short transport distance. In other words, all the sizes were mixed together and then they just dropped out all of a sudden. Right? So here's a glacial deposit, poorly sorted. This is a glacial moraine. And you've got a lab exercise with glaciers that talks about these moraines and what they are, how they form. So I'm not going to go into those details right now. You'll get that in primarily in the laboratory exercise. But you also have information in your textbook, I believe, on nope, just through the lab. We'll talk about glaciers in the lab. Stratification or bedding, layering of the rock that develops as a sediment is deposited. That's what bedding is, the definition of bedding. The bedding can be very obvious. You can see it from a great distance. It may be very thick, very massive, or it could be in thin layers, which takes a little closer inspection. Most bedding is horizontal, at least when the rock is formed. When the beds are laid down, it's horizontal because it's responding to gravity. Gravity is causing it to drop out, and gravity acts in a vertical direction toward the center of the earth. So it tends to cause the same thing to happen at various layers. Now, this bedding may be modified in the process of forming the rock, and it can be tilted, or it can be bent, it can be fractured. Anything can happen. But originally, the bedding is horizontal. We can get cross bedding as a consequence of strong wind or current action. So if you get strong currents of any kind, you can blow the sediments up and pile them up one layer on top of another, sideways. You can get angular bedding. Even before the rock forms, you can have cross bedding. Here's an example in sandstone in Zion National Park in Utah. How about fossils? Very often, the most distinctive and interesting part of sedimentary rock is fossils that may be embedded, right? You don't find fossils in igneous rock because everything is melted first. It's destroyed before the igneous rock forms. And metamorphic rock doesn't preserve fossils either because the pressure and temperatures are much too high. So fossils are exclusively found in sedimentary rock. We'll look in chapter 24, we'll look again at fossils and how we can determine age of the fossil and or the rock in which it's embedded, various methods of doing that. So we won't spend time on it right now. So here we have footprints that were mentioned earlier, footprints and fossils embedded in the sedimentary rock. Right? Those are dinosaur footprints. These are dinosaur bones. Metamorphic rock. Okay, so we've talked about igneous rock, we've talked about sedimentary rock. Now we're going to look at metamorphic rock. We take metamorphic last because metamorphic rock can be formed from igneous or sedimentary rock. All right. So those are just refreshers on definitions. And the conditions required to form metamorphic are somewhere in between sedimentary and igneous. If it's too shallow, then the metamorphic process will not occur. There's not enough heat and pressure to do it. If it's too deep, then the heat and pressure is enough to melt the parent rock, and now you don't have metamorphic anymore. You've got igneous. So it's kind of an in-between layer, so to speak. Metamorphism is a general term for the process that describes the conversion of rock without melting. That's important. There is a conversion process for metamorphic, but melting is off limits. And you can metamorphose any type of rock. In fact, You can metamorphose metamorphic rock. It can be metamorphosed one time and then down the road, metamorphosed again. The primary agents are heat and pressure, but you can also get chemical activity that can contribute to this metamorphic process. All right, so what does each do? Well, heat and pressure tend to break down minerals. They break bonds. If you put energy into a bond, eventually, if you get enough of it, you'll break the bond. So when it reforms, it may form something different. That's a metamorphic process. Whereas fluid movement through the rock can also pick up and move ions from one place to another and redeposit them. That is also a metamorphic process. So when we talk about metamorphism, we describe the parent rock, that is the rock from which the metamorphic rock was formed. And that is another contributing factor to determine the outcome of the metamorphosis. What did it start as? Did it start as granite, right, an igneous rock with its composition? Or did it start as some sedimentary rock which would lead to a different result? Even under the same conditions for each one, you would get a different result. Okay. The metamorphism can change the texture, the size of the crystals. That's obvious. It can also change the mineral composition of the parent rock. So it can either maintain the elemental ratios and just rearrange them, or it can move some of those elements out, leave some behind, and restructure those. So really metamorphism, the sky is the limit. You can do lots of different things. Or it could only change one or two. Okay, these are examples. We can generally classify metamorphic rocks into two categories: the foliated rocks and the non-foliated. Okay, we'll have to define what that means. But here on the left-hand side, we're introduced to the parent rock. So shale, remember, formed from muds as a sedimentary rock. If we put it under pressure and temperature, we can form slate. Right? And slate is, generally speaking, much more durable, harder, denser than shale. The key minerals has clays in it. It has quartz, mica, which is a two-dimensional silicate, or chlorite. It's very fine grain. It has definite cleavage. And that's characteristic of all the foliated rocks. They show you some type of cleavage available. If we take shale or basalt or slate, see, here we go. We can take slate and metamorphose it again. So any one of these three can produce a schist. Okay? And we get different mineral structures, possible minerals in here. It's very coarse grained and well foliated. Let me see, what do they mean by that? Okay. Folia comes from the Greek root word for leaf, which is flat. But it doesn't necessarily mean that they flake. I mentioned cleavage here. Cleavage is not necessarily part of the others. All right, that I misspoke there. It can produce cleavage, but foliation is on the microscopic scale. You can see layering in the grains. And this is generally due to show you the direction of pressure. Right? So if it's foliated this way, pressure was applied that direction. So when the minerals restructured, they restructured in these layers. And they can either be well foliated or not so well foliated, or not at all. So if we take shale, granite, slate, even schist, okay, so we're going to do a double metamorphism, slate to slate, shale to slate, and slate to schist, and then schist to gneiss. Right. So you can get multiple metamorphic episodes in these foliated rocks. Non-foliated rocks. If we start with limestone, there's calcium carbonate, and metamorphose it, you get marble. And the key mineral there is calcite. Okay, so marble has the same composition as limestone, except its structure has been changed under pressure and heat. Sandstone, if we metamorphose sandstone, we can get quartzite, whose key mineral is quartz, obviously. If we take shale from the parent rock up here, and we get a non-foliated metamorphic process, we can take shale to hornfels or basalts or any other fine-grained rock. We can produce a mineral that's mica or quartz. Right? So there are multiple possibilities here. Okay, what if the parent rock only contains one mineral? The metamorphic rock will also be composed of that same mineral. It may rearrange the mineral, but it's generally speaking, if there's only one mineral to start with, that's where you end up with. Example, limestone. Its mineral is calcium carbonate. Marble, its mineral is calcium carbonate. After metamorphosis has occurred. Just changes the structure, does not change the chemical composition. These are fossiliferous limestones and marbles. So these particular limestones have incorporated in them unmodified sources for the limestone. In other words, these shells are composed of calcium carbonate, but they haven't been, they're conglomerates in this type of limestone. But when you put it under pressure, you get marble. Right? So you no longer see the fossils. Now this marble happens to show the bedding process from the original limestone. Right? And you can see that under pressure, the compaction has occurred and modification of its structure. If you look at it under a microscope, you can see that, or even a magnifying glass will tell you. So when we change sandstone to quartzite, that's a metamorphosis of a rock that contains only one mineral. Right? Sand is basically silicon dioxide. So when we metamorphose it, we get quartzite. Right? All we've changed is the structure. Now, if the parent rock is composed of several minerals, the process of metamorphism may create a new collection or a suite of different minerals, in addition to structural changes. And that's in response to the heat and the pressure. So shale, the parent material, is very fine grained. It has a mixture of quartz, clays, some micas, right, the two-dimensional things, and chlorite. So under pressure and temperature, we can change shale into slate, which is a different collection of minerals. We can go further to schist. We can go further to gneiss. And each step of metamorphosis changes the collection of minerals and their structure. All right, here's gneiss. Right. Gneiss is typically considered a very, very hard stone, very durable stone. So if you make a headstone for a grave marker out of gneiss, it's going to be there for a very, very long time. And any carving you do into it with great difficulty for your instruments will be there for a very long time. Okay, so here's a correlation of what happens to shale when you subject it to pressure and temperature. So in the beginning, shale is primarily the quartz particles. When we modify it by metamorphism to slate, low-grade slate, we get, we still have some quartz. We have these other minerals, plagioclase, chlorite, mica. Not likely to have some garnet in there. Then when we convert it to schist, we still have the plagioclases. We still have some chlorite. We get more mica. We start to develop garnet, which is another type of mineral, not just a gemstone. It's a bona fide mineral. Kyanite, I don't know what that is. And then we start to develop some sillimanite. When you go to gneiss, you still got the quartz and the plagioclase, but the chlorite's gone, most of the mica's gone, and you start to favor garnet. And you still have a little bit of kyanite. Now you've introduced this new mineral, sillimanite. If you get hot enough, then game's over. Now you got magma. Okay, so we've mentioned metamorphism in terms of heat and pressure and some chemical activity. But for practical purposes, we can subdivide metamorphism into based upon the mechanism of the metamorphism itself. So is the metamorphism due to contact of different rocks on shear? Is it direct pressure? Is it due on shear? Or is it a regional phenomenon? And so how do we distinguish these two? Contact metamorphism. That occurs when magma comes into direct contact with the parent rock. So that doesn't necessarily mean that the parent rock will melt. But remember when magma intrudes into sedimentary rock, for instance, wherever the magma contacts the sedimentary rock, it increases the temperature way, way high. but it may only melt the surface, and further into the rock, it's cooler, but there's enough temperature to start changing it. So you get this layer around that pluton that is metamorphic in nature, as contact metamorphism. So the pressure hasn't increased significantly, only temperature. And tends to form coarse-grained crystals where it's in contact with the magma. So these are clues that can tell you how the rock was formed. Now, in that respect, the study of geology is just one huge detective story. And as we move away from the magma, the rock becomes progressively finer grained. Contact metamorphic zone occurs when a parent rock is intruded by molten magma. That just restates the obvious. Okay, shear metamorphism results from the intense pressure that exists along active fault zones where rocks slide past one another. You may have heard, I don't know if you have or not, heard of a process called friction welding. Friction welding was used to build spacecraft because what you needed was a very good weld. That is, these two pieces need to be as one. But you could not guarantee a good weld with precision dimensions simply by putting them together and then hitting them with a welding rod and then grinding them off. The imperfections would have been too dangerous for spacecraft. Plus, most spacecraft have very thin metal pieces, and welding rods, just the environment's too harsh. So friction welding was invented. So if you put two pieces of metal together in this example, and you push them past one another, the friction heats them up, right? You can do that if you move your hands back and forth. Your hands get warm. So if you push them past one another under sufficient pressure, and you consider, they'll eventually partially liquefy and weld together. That's the idea behind shear metamorphism. These rocks are being pressed against each other under high pressure, and they're being forced past one another. So there's lots of friction. Heat develops, right? So they don't have to be really deep, but the friction supplies enough heat under that pressure to metamorphose the rock in that zone, along this fault zone. You often get deformation, right? Uneven bending, for instance, of the rock, and definitely recrystallization of the minerals, resulting from this added heat and pressure. Okay, now what do we mean by regional metamorphism? Contact makes sense. Shear makes sense. But what does regional metamorphism mean? Well, it definitely affects large areas. And it's caused by a combination of high temperature and high pressure. So this must occur at just the right depth and just the right temperature over a large area. Very often, this is due to deformations resulting from mountain building. In other words, lots of pressure and heat built up as the forces underneath push and build the mountain. This occurs at convergent plate boundaries. When plate boundaries collide with one another, either one dives underneath the other and pushes this one up, in which case you can get some metamorphism there, or where plate boundaries, continental plate boundaries both, impact each other and they buckle, like the Himalayan mountains. So these convergent plate boundaries are, generally speaking, common zones for this regional metamorphism. Okay. Foliation is typically observed in regional metamorphic processes. This is because when these impacts occur on a regional scale, you get very high pressures, and the crystal structures, the grains, the mineral grains, align themselves parallel to the forces, to the arrangement. So if the forces are this way, the grains will be aligned that way. This is called foliation. And that's what we observed in those metamorphic rocks in that previous table. One characteristic is the pressure must be very, very high. You don't have to have high temperature, but the pressures are extremely high. And the foliation is a clue to the fact that the pressures must have been very high in order to align the grains in that leafy layer structure. If the rock forms at high temperatures, but not particularly high pressures, you will not see foliation, because temperatures tend to cause randomization of the mineral particles, whereas pressure tends to align them. We see this in shale as good examples of foliation. So when you, now the shale is the parent material. So if you take shale, which has good cleavage in it, you can flake off pieces of shale. When you put it under pressure and form slate, you still have those, you create more of that alignment, foliation of the crystal structures. And if you're going to use the slate for building purposes, then you can also split the slate along those grains and form thin sheets. So you can form slate roofs. You can split in larger pieces and make a pool table out of it, for instance. Okay. Schists are the next step beyond slate, and they are foliated, but they have larger visible grains than the slates. So as you modify, you start to modify the crystal structures and grow the grains bigger over time under extreme pressure, not high temperature, pressure. The gneisses take this foliation even further, and the gneisses tend to form very distinctive bands. In fact, if we go back and look at that headstone, let's see, how far back do we have to go? There we go. You can see these visible bands forming in the gneiss as an outcome of a metamorphic process. Okay. Now, how about hydrothermal metamorphism? This is a chemical alteration based upon the introduction of hot water. Hot water is very reactive. In fact, if you've ever seen a greasy, dirty engine cleaned with a steam hose, right? I've never done it, but I've watched it. You want to stand back because that steam is under high pressure and very hot. It could kill you, actually. So what is that steam doing? Well, generally speaking, as the temperature of water increases, the solubility of any materials in it increase. So the hotter the water gets, the more materials you can put in solution. This goes for not just for the grease, which actually goes into solution in the water. It isn't just blown off, melted off. It goes into solution in the steam. So if this hot water under high pressure moves into a rock, it can dissolve some of the minerals and move them from one place to another. And if it's carrying any minerals of its own, it may carry away some from the parent material, parent rock, and deposit some that it's carrying in. So replace them. Now, where does this usually occur? Hydrothermal metamorphism usually occurs at divergent boundaries on the ocean floor, where there is abundant hot water. Right? There's not a lot of pressure, except the overburden of water supplies some pressure. But the hot water, very hot water, and the hotter you get water, the higher the pressure, say deep in the ocean, the hotter you can get water before it boils. Okay, so that's it for minerals, rocks, and volcanoes. Our last topic.